Okay, so our last lesson in our probability unit is on compound events, which is a little bit trickier. Okay, what is a compound event? A compound event simply is the probability of two or more events happening at the same time. So your big word that you're going to kind of look for will be the word or here. In the previous lesson, it was the word and. Okay, anyways, suppose your friend Kaya misses the bus to class half of the time. She also forgets her homework 1 out of 5 classes each week. What is the probability that Kaya misses the bus or forgets her homework? So that's an example of a compound event. Now, compound events you've done before, especially if they've been mutually exclusive, you've probably done them before. So these are mutually exclusive. You'll see here in this Venn diagram right here, these are two events that don't have any intersection. They don't have anything that overlaps. In other words, for probability, these would be events that cannot both happen at the same time. So an example would be like rolling a 1 and rolling a 2 at the same time, or at the same time on a single roll. Obviously, when you roll, you can get a 1 or a 2, but you can't get them both at the same time. So if I say, all right, what's the probability of rolling a 1 or a 2, you probably understand here that I would just need to add those together. So what's the probability of rolling a 1? You would say 1 out of 6. What's the probability of rolling a 2? 1 out of 6. So getting a 1 or a 2 should make sense to you that the probability is 2 out of 6, right? And that's all there is to it. So you've done that before. So if it's mutually exclusive, you can just add them together. Okay. So here is a problem that kind of takes a look at that. A group of students is donating blood during a blood drive. A student has a 9 out of 20 probability of having type O blood and a 2 out of 5 probability of having type A blood. Why are these events mutually exclusive? Well, you can have type O or type A or a couple other different types of blood, but you can't have them both at the same time. So that's why it's mutually exclusive. So there's no overlap with those. So we would simply add these two probabilities together. I would go 9/20 plus 2/5. Remember, when we add, we have to have a common denominator. So this would be 8/20. If I add that, I get 17 out of 20, which is reduced, or you could change it to 0.85 or 85%. So given this circumstance, you have an 85% chance that they have type O or type A blood. Okay, that's not too bad. Now, inclusive events is a little trickier. This is where they have an overlap. So inclusive events, you can see here, overlap with the Venn diagram. They have one or more outcomes in common. An example of this would be like if we're looking at what is the probability of getting an even or a prime number, rolling a 2, or rolling a prime number on the same roll of a number cube. Well, since 2 is prime, there's an overlap. For here, even and prime, if I was going to say what's the probability of getting an even or a prime number, well, even numbers would be 2, 4, and 6, right? Prime numbers are numbers 2, 3, and 5. Okay, so now if I just added those up, you'll notice that I'd be double counting 2. So I'd be counting it twice, and we don't want to double count it, so that's why we would then have to take away that one case. So I would say, well, 3 out of 6 if it's even, 3 out of 6 are prime, but the number 2 is in both of those, so we'd have to take that out. There's 1, 2, and so we would subtract that, so we don't double count it. In other words, we're not counting this second 2. You'll notice that there's 5 then. And that's when we do this down here. 3, 6 plus 3, 6 is 6, 6 minus 1/6 would be 5, 6. And that's what we got up here, 5 of them, right? So mutually exclusive is pretty easy. Inclusive, you got to be careful that you're just not double counting, and that's why we subtract that part. Okay, so we're going to take a look at a couple of inclusive events. And you'll probably see pretty quickly why these are inclusive, right? Rolling a 4 or an even number. Well, 4 is even, so it's in both categories. That's why it's an inclusive event. Okay, so I'm just going to say, well, probability of getting a 4 then, which would be 1 out of 6, plus the probability that it's an even number on a number cube would be 3 out of 6. But then since 4 is in both categories, I don't want to double count it. I'm going to take that 1 away. So really, I'd end up with 3/6 or a half. Okay, I hope that makes sense. Let's try another one, just kind of make sure we got it. Rolling an odd number, okay, so that would be 1, 3, and 5 on a number cube, or a number greater than 2. That would be 3, 4, 5, 6. You'll notice there's an overlap. The numbers 3 and 5 overlap. So that's why, again, this is inclusive. So probability of getting an odd number would be 3 out of 6. Probability of getting a number greater than 2 would be 4 out of 6. And then we want to take away overlaps. 3, 5, 3, and 5. So there's 2 of them that overlap, 3 and 5. So I want to take away 2 out of 6, which that would give me 5/6. Okay. Hopefully this is starting to make sense. Okay, a card is drawn from a standard deck of 52. Find the probability. Find the probability of getting a red card, which is just hearts or diamonds, or a face card, jack, queen, or king. So a red card, there are 13 hearts and 13 diamonds, so that's 26 out of 52, or half the deck. Plus a face card. Remember, there's 4 of each of these. 4 jacks, 4 queens, 4 kings. So that's 12. Now I want to take away the ones that are both. So there's 2 red jacks, 2 red queens, and 2 red kings. So that's -6. Okay, 26 plus 12 is 38, minus 6 is 32 over 52. And 32 divided by 52 gives me about 0.615. So we'll say approximately 0.62. You could reduce that fraction as well if you wanted. I'm just going to leave it in decimal form. All right. Okay, let's take a look at a situation where you might want to organize a little bit trickier problem in a Venn diagram. So this says, of 1,560 students surveyed, 840 were seniors and 630 read a daily news source. The rest of the students were juniors. Only 215 of the news readers were juniors. What is the probability that a student was a senior or they read a daily news source? So you'll see at the top I wrote 1,560. That's the total number of students. And then here, seniors, my purple circle is the total number of seniors, 840. My green circle is the daily news people, 630 read a daily news source. Okay, now only 215 of the news readers were juniors. So it says if you weren't a senior, then you're a junior in this poll. So that means 215 have to be in just this section here. They can't be in this because that's where they're seniors and daily news. But if they're just a junior, then they would be there. Okay, so that's 215. Now this whole circle here has to add up to 630. So if I go 630 minus 215, that gives me 415. That would be what's left in my circle in the middle. So I'm going to write that in the middle. That goes there. Okay. So, cool. Now, The purple circle has to add up to 840. Well, I already have 415 in the middle. So people who are only seniors and don't read the news would be 840 minus 415, which is 425, right? Okay. Now, what is the probability the student was a senior or read a daily news source? Now, if you do the Venn diagram and you've separated it out, you're not double counting. So you can just use these numbers here. So you can just add them up. If you add those numbers up, 425 plus 415 plus 215, you get 1,055. So that would be the over 1,560. Now, if we simplify that, that's about 0.676. So we'll say about 0.68. Okay. So that's one way to do it. If you use the Venn diagram, you can simplify it that way. You can also use the formula. So let's try the formula way and see how that goes. I'll do this one in just like a blue, something that we didn't do before. Okay, so then you would say probability that you're a senior is 840 over 1560 plus daily news readers, 630 over 1560. And then we would need to subtract the ones that are both. So you would still need to figure this number out. Now, we've already done it on our Venn diagram. So you can do the Venn diagram and use it this way and still do the formula. Or you can do it the other way that we talked about. Now, if I go 840 plus 630 is 1,470 minus 415 is 1,055. And then on the bottom, I'd still have 1,560. Notice we still get the same answer. So either way you go is fine. You use whichever one makes the most sense. But sometimes with these more complicated problems, it's a little better to organize your data in a Venn diagram. Okay. Okay. So also you can get some pretty challenging compound events. So sometimes it's best to work backwards. So let's take a look at this problem. It says, each of 6 students randomly chooses a butterfly from a list of 8 kinds of butterflies. What is the probability that at least 2 students choose the same butterfly? Okay, so this one, it might be easiest to work backwards. So the probability at least 2 students choose the same one is probably easier to say, well, what's the probability that they all choose a different one first? And then take it away from 1 or 100%, right? So let's figure that part out first. The probability that they all choose a different one would be the total number of ways 6 students can choose different butterflies over the total number of ways 6 students can choose a butterfly, period. So let's start with the bottom number. Okay, the first student has 8 possibilities. Okay, so total number of possible butterflies, we have each student has 8 choices. And there are 6 students. So total number of possibilities here would be 8 times 8 to the 6th power, in other words, which is a big number, 262,144. Okay, now, how many ways can they choose different ones? Well, if they're going to be different, the first student has 8 choices, the second student has 7, then 6, then 5, then 4, then 3. Okay, now if we do that, I've done this already, so I'm just going to show you. you get this. You get 20,160 over 262,144, which is about 0.0769 or almost 8%. Okay, so that's if they all choose it differently, all different. You have about around an 8% chance of that happening. So that means I would just take that away from 1, and that would tell me the chance that they all, at least 2 students, choose the same butterfly. So that would be 0.92, right? 0.9231. About a 92% chance that at least 2 students are going to choose the same butterfly. And hopefully that kind of makes sense. This is a little bit more complicated one, but sometimes with those more complicated ones, it's best to just work backwards. Okay, there's our probability and work on this assignment. Good luck.